Hello.
Hey.
Hope you guys had a nice weekend.
Yes.
Awesome. Hopefully you read the announcement that I made after class last time, because I wrote something completely wrong. But if you didn't, just to recap, we had a measure of angle A at the end there was equal to the sum of two measures, measure of angle 1, measure of angle 6. And I actually rewatched the video. I did say the right thing, and then I wrote something that was completely wrong. But the conclusion here is that if angle A is the sum of these two angles, then they both can't be bigger than 1/2 of the measure of angle A. Right? If they're both bigger than 1/2 of the measure of angle A, then this equality could not possibly be satisfied. So either measure of angle 1 is less than or equal to 1/2 of measure of angle A, or measure of angle 6 is less than or equal to 1/2 of measure of angle A. And that was what I meant to write. So if you have the other version in your notes, I believe I wrote this: measure of angle A was less than or equal to 1/2 of measure of angle 1. So we were writing it the wrong way around.
Then you had it for 6 later on, yeah.
Yeah. And you guys were looking at me at the time like you were very confused, and now I understand why. So. So anyway, so we have that. So that was the famous Securius theorem. It says angle sum of a triangle is less than or equal to 180 degrees, every triangle. But we started off the section with Securius Quadrilaterals, right? Remember, Securius was looking at these quadrilaterals, and he was attempting to prove Euclid's fifth postulate by ruling out certain cases that the two what are called summit angles, the two angles of the autologous quadrilateral, have to be 90 degrees. And we can rule out the obtuse case right now using the Securius theorem. So, quick corollary: the angle sum of any convex quadrilateral is less than or equal to 360 degrees. Alright, so this rules out, the hypothesis of the obtuse angle. Alright, maybe I should remind you of this. So Securius Quadrilaterals look like this. You've got two congruent sides, two perpendiculars here, and Securius had proved that these two angles must be congruent. And he had three cases. Either these angles are less than 90 degrees, equal to 90 degrees, or larger than 90 degrees. Well, if the angle sum of a quadrilateral has to be less than or equal to 360, then these guys cannot be bigger than 90 degrees, right? So that rules out the obtuse angle case. And the other two cases, the acute angle or the right angle case, you can't rule them out because they're true in neutral geometry. Fairly easy proof, so hence why it's called a corollary. It's an immediate corollary of Securius theorem. It should follow rather readily. Let's see. Let's just say I'm going to rely on a picture here, so I don't have to label a whole bunch of stuff. Consider the convex quadrilateral. Consider the convex quadrilateral A, B, C, D shown. Alright, so we'll just draw the convex quadrilateral A, B, C, D. What's the angle sum of this convex quadrilateral? Well, it's the angle sum of A plus B plus B plus C plus D, right? So just add them all together. So the angle sum of A, B, C, D is equal to measure of angle A plus measure of angle B plus measure of angle C plus measure of angle D. Well, now let's slice it. As we always do with quadrilaterals, we'll slice it into triangles because everybody loves triangles. And we'll just, any diagonal that you want. This is convex. This is where the word convex comes in. Convex guarantees that I can draw diagonals that are inside the quadrilateral. So how about I just cut it this way. And we'll label these angles. So now I'll call these angles 1, 2, 3, and 4. Again, this is where I'm not sort of writing down exactly what these angles are. It's just we'll rely on the picture. I've already referred the reader to the picture. And let's break these into pieces. So measure of angle A is angle 1 plus angle 4, right? This is measure of angle 1 plus measure of angle 4. We've got angle B that we haven't changed. We've got angle C that's two angles now. Measure of angle C plus measure 2 plus measure of angle 3, and D measure of angle D. Can you see where I'm going with this? Now I'm just going to group them into triangles. I'm going to group these into appropriate triangles. 1, 2, and B is a triangle. 4, 3, and D is a triangle. Both of those individually add up to less than 180 or equal to 180. So we'll group these. We've got measure of angle 1 plus measure of angle 2 plus measure of angle B. There's a triangle. And measure of angle 4 plus measure of angle 3 plus measure of angle D. That's a triangle. Securius Quadrilateral says this sum has to be less than or equal to 180. Securius Lejeune? Securius Lejeune says both of these have to be less than or equal to 180. And the proof is done. So it is an immediate corollary, right? Once you know the angle sum of triangles is less than or equal to 180, well now you can do this trick that you always do with larger polygons, at least convex polygons, is break them up into triangles. And then look at the angle sum of those triangles to find the angle sum of the whole thing. Any questions? Alright, so that rules out the obtuse angle case, the hypothesis of the obtuse angle. But of course, Securius could not rule out the acute angle case because he just can't do it. But we'll move on then. Securius Quadrilateral was a sort of a big deal because rectangles are a big deal in hyperbolic and neutral geometry. And it was something people studied for a long time when they were first getting their feet wet with this hyperbolic stuff. So 3.6 we'll call this section the search for a rectangle. Again, because this actually turns out to be equivalent to Euclid's fifth postulate, if a rectangle exists, then Euclid's fifth postulate is true. So there are lots of people out there, Securius is one of them, looking for, can I construct a rectangle? Can I prove that the hypothesis of the acute angle is false? And it turns out you can't, but we'll do lots of stuff with rectangles in this section. So I'd like to introduce a little bit more terminology. I literally just had Securius Quadrilateral on the board here, but we'll introduce a little bit more terminology that are used. So recall Securius Quadrilateral once again. I'd like to draw this in a hyperbolic sense. Let me draw this hyperbolically. So this should really connect. I'm going to draw this with curvy linear sides, so it looks sort of hyperbolic. But this is again Securius Quadrilateral. He's got a perpendicular cutting across the two sides there, and two sides that are congruent. And yeah, the terminology I want to introduce is just this. So this side here that's perpendicular to both of these congruent sides, he calls this the base. And the top along here, he calls this the summit. Of course, we've got these two angles. He proves they're congruent, and he calls those the summit angles. Summit angles. So Securius proves that that the summit angles are congruent, as we've seen. I actually reproved that for myself over the weekend. The proof I gave you last class was cutting down the middle and using SAS, which actually was a really nice proof. I redid it by Tony, as you suggested, doing diagonals and stuff, and it's a lot longer of a proof, but you can get there. He proves summit angles are congruent. He proves lots of other things. He proves, for example, diagonals. If you draw on both diagonals, those must be congruent to each other. He has lots of results here. I just want to go through one of them. So, in any Securius quadrilateral, music is kind of relaxing to do math too. In any Securius quadrilateral, the length of the summit is greater than or equal to the length of the base. So I don't really find this to be a particularly interesting statement in terms of Securius quadrilaterals. These Securius quadrilaterals don't particularly interest me, but it says something much more profound about lines, right? Lines in general. It says if I have two lines, this is in the Euclidean world, and I have a transversal that cuts through them perpendicularly, and then I go on these parallel lines and I go sort of the same distance out on both of them, and I measure that distance between those 2 points. Well, in the Euclidean world, they'd be the same distance apart, right? But in a hyperbolic sense, if I have a transversal that cuts through perpendicularly, and I go the same distance out on both lines, and then I measure the distance between them, well, those distances, these lines, in a sense, are getting further apart, right? They're spreading apart. So this is sort of why this interests me, is it tells you something about how lines behave in hyperbolic geometry.
There's no such thing as a straight line hyperbolic, right?
It's not that there's no such thing as a straight line, it's just it doesn't look straight, sort of when you draw it Euclideanly. But straight lines are just sort of distance minimizing lines, right? If I have 2 points in hyperbolic geometry, there's a line between them that minimizes the distance,
Yeah.
and that is a straight line.
Okay. Hmm.
It just so happens that straight lines, sort of parallel lines, get further apart as you travel down them, which is, or closer together, which is weird. Yeah, so let's prove this. It's a proof by cases. So how about we call this a sketch, so I don't have to write down a whole bunch of details. We'll just call it a sketch, and we'll draw a picture. Here's A, B, C, D, and we've got 2 congruent sides, and I'm going to cut through a diagonal. I'm also going to give you some angles here. This is angle 1, this is angle 2, and this is angle 3. And I'm going to observe that because this is a Securius Quadrilateral, measure of angle 2 and measure of angle 3 is 90 degrees. And what do I want to show? Well, the theorem claimed that the base is always shorter than or equal to the summit. So I'm trying to show that AB is less than or equal to CD. Right? So we want to show AB less than or equal to CD. And there's 3 possible cases. So we have 3 cases. Kind of an interesting proof because it's not the first thing that jumps out to what we're, not the first thing that jumps out to what I want to do, but I'm going to compare measure of angle 1 and measure of angle 2. All right, so here's the 3 cases. 1, if the measure of angle 1 is less than, not measure of angle 2, I've labeled this differently than I have in my notes, I'm comparing to measure of angle 3. Okay, if measure of angle 1 is less than measure of angle 3, oops, that wouldn't be less the case. Then what happens? There's a theorem we had that I can immediately invoke here. These 2 sides are congruent, right? AD, BC, those are congruent. These are the same length, so I have a hinge. I have 2 hinges here that are the same. I've got this hinge, ADB here, this angle if you want, and this hinge here that are exactly the same. The Hinge Theorem said if this angle is smaller than this one, then this side has to be smaller than this side. And so I can immediately invoke the Hinge Theorem. If this is true, then by the Hinge Theorem, I don't know why I've capitalized theorem there, but by the Hinge Theorem, we have the desired result. We have AB is less than or equal to CD. All right, so that was easy. How about second case? If the measure of angle 1 is equal to the measure of angle 3. What happens now? I suppose technically you could invoke the Hinge Theorem again, right? Hinge Theorem would say they're the same length, but how about instead of invoking such a fancy result, how about we just go with SAS and SAS? These 2 triangles are congruent, so these sides have to be congruent. And by SAS, we have triangle ADB is congruent to triangle, what is it, CBD. So once again, we have the result. AB is equal to CD, which is allowable, right? We just have to prove it's less than or equal to CD. And the third case is the most tricky, but still not particularly hard. If the measure of angle 1 is greater than the measure of angle 3. Well, what would happen here? Again, you could think about the Hinge theorem. The Hinge theorem would say this side is longer than this side. And I'm trying to prove that that can't be the case. So what I'm actually looking for is a contradiction. Right? I'm trying to prove that this actually can't happen. How do we do this? Then, measure of angle 1 plus measure of angle 2. Add them together. Well, measure of angle 1 is bigger than angle 3, right? So measure of angle 1 plus measure of angle 2, that's bigger than measure of angle 3 plus measure of angle 2. Measure of angle 2 plus measure of angle 3, that's 90 degrees, right? Where's the contradiction? I have that this angle plus this angle is bigger than 90. Plus this angle. Yeah, so that's bigger than 180. So now I have a triangle with angle sum bigger than 180. That contradicts the Securius Quadrilateral theorem, right? So this implies that the angle sum of triangle ABD is bigger than 180 degrees. Contradicting Securius Quadrilateral. So either case 1 or case 2 is true. And in either case, the base is shorter than the summit. I won't write anymore because we call this a proof or a sketch, so we'll just add in the proof there. Again, an interesting proof, I think, because it's not the most obvious way to prove this, that you just want to compare these two angles and look at the possible cases there to conclude about the lengths. But once you have that, once you have this comparison, then it's actually fairly easy to go through the cases. Any questions? All right, that's all I really want to say about Securius Quadrilaterals. There's a lot more, a lot of simple results. Most of them follow just by doing stuff with triangles. Maybe I'll assign a few for homework. There's another type of quadrilateral that was pretty well studied that, again, I don't really want to say anything about. I might assign a few problems for homework. But I might as well just tell you what the quadrilateral is. So, we also have Lambert Quadrilaterals that I will sort of relegate to homework assignments. But I will expect you to know what they are in case on the next exam I ask you a question about Lambert Quadrilaterals or something. So I might do a few homework assignments for them. And pretty simple. Lambert Quadrilateral is a quadrilateral with 3 right angles. So Lambert is a fairly well-known mathematician, not as well-known as some of his contemporaries who were also alive in the mid-1700s. But I believe his biggest claim to fame was he was the first person to prove rigorously that pi is irrational. So fairly decent claim to fame. But he was doing basically the same thing as Securius. He was looking at these types of quadrilaterals, and he's asking about what's that fourth angle. Again, he could prove that this angle cannot be obtuse, right? Because that would violate the fact that in neutral geometry, quadrilaterals have less than 100 or less than 360 degrees. But he also could not rule out the acute case because you can't do it in neutral geometry. Unlike Securius, he did not throw his results away. He did not say this is all absurd. He realized there's something going on here. This is sort of, I'm studying a new type of geometry. In fact, I believe he realized something about the fact that if this was obtuse, then there's some connections here with spherical geometry, which is really what happens. So, in any case, this is a Lambert quadrilateral. I might suggest a few homework problems based on these things, but I don't want to spend too long working on this, so we'll move on. There's a lot in this section that I won't particularly cover because it's a very long section. But a quick definition, I'm sure you already know this, but a rectangle, when I'm talking about rectangles, a rectangle is a quadrilateral with 4 right angles. Quadrilateral with 4 right angles. And now there's lots of results here with rectangles, and they all sort of start like this. If a rectangle exists, then we can do the following. The problem is, does a rectangle actually exist or not? Well, not in hyperbolic, but we'll prove some stuff here. Sorry if I erased that too fast. A rectangle is a quadrilateral with 4 right angles. Here's the first theorem. If one rectangle exists, then there exists a rectangle with an arbitrarily large side. Might not seem that profound to you, but it's sort of a big deal. If a rectangle exists, then you can produce as big a rectangle as you want, at least along one side. The proof, the idea of the proof is going to be very simple. We're just going to take our rectangle that exists, and we're going to sort of stack them together and make it as long as you want. Okay? We just have to prove that this is a valid process.
Right.
Yeah, that when you stack them, you still end up with 4 right angles and so on. So let's proceed. How am I going to make it arbitrarily large? Well, I'm just going to say, you give me a line segment. I'm going to construct a rectangle with a side longer than your line segment. And that establishes, okay, we can do this sort of in an arbitrary sense. So let PQ be any line segment. We want to show that we can construct a rectangle with one side greater in length than PQ. Think about notationally what I should use here. Am I saying it's greater in length than the side itself, or am I saying it's greater in length than the measure of the length of the side? Should I have a bar on top of this? I don't know. I don't think it matters either way. Right? I think both interpretations work fine. So anyway, let's let ABCD be a rectangle. This is an important catch. In most proofs that you do in neutral geometry, you cannot say this, right? I can only say this because part of my assumption is a rectangle actually exists. So let ABCD be a rectangle, and let B2 be a point. So I'll draw a picture in a second. Be a point on the extended ray AB, so that A, then B, then B2. And so that AB is congruent to B, B2. So I'm going to draw a picture, but let me just finish writing all the details here. Also, similarly, let C2 be a point on CD. Actually, it shouldn't be CD. It's not pointing this way. It would be DC. There we go. So that D, then C, then C2. And so that CD is congruent to C, C2. I'll give you a second to catch up. All right, so what am I doing here? I'm saying, let's start off with a rectangle. We've got A, B, C, D. It's a rectangle, so all of these are right angles. And we've gone in, we've said, okay, let's take this line segment AB, let's extend this. We'll look at the extended ray. We'll look at the extended ray AB, and we'll find a point on this ray B2 that's on this ray, and so that B2 is the same distance from B as A is. And then we did the same thing up top. We said, okay, let's take the ray DC, we'll extend it in the direction of C, and we'll choose a point on this ray C2 that's the same distance from C as D is. And how about we just draw in, or dot in that part there, C2 and B2. What I want to claim is that these are still right angles. How do I establish that? Well, these are supplementary angles here, right? This one's 90, so this has to be 90. That one's 90, so that has to be 90. How do I show that these are right angles? Yeah, SAS, right? I've got two quadrilaterals, S, A, S, A, S. So by SAS, these are congruent, and because they're congruent, the corresponding angles here and here and here and here have to match up. So by SAS, A, B, C, D is congruent to, let's try to get this right, B2, BC, C2. B2, BC, C2. And what that means is we've constructed a bigger rectangle. We've constructed a bigger rectangle, A, B2, C2, D. A, B2, C2, D is a rectangle. How long is one of the sides now? Well, we'll take, we'll say with the side AB2 with side length AB2. How long is that? Well, AB and BB2 are the same length, so AB2 is just twice the length of the original side. This is just 2 times AB. This is obviously a repeatable process, right? I can do this again. I can just tack on another another piece and make this longer and longer. So repeating the process n times gives a rectangle A, B, N, C, N, D with side length ABN equals N times AB. And of course, you can make n as large as you want, right? So I can make an arbitrarily large rectangle. How am I going to formalize this? Well, we started off with a line segment PQ, and I said I'm going to construct a rectangle with a side longer than PQ. So let's just say choose n sufficiently large now, right? So choose n sufficiently large so that ABN is, which is equal to n times AB, is bigger than the length of PQ, and we're done. Now you might say, hold on, that doesn't mean I can construct an arbitrarily large rectangle. It just means I can construct an arbitrarily long rectangle, right? But now you can just repeat the process. Now you can make it arbitrarily long in one direction, and now if you want to make it arbitrarily large, well now just repeat the process by stacking them this way, right? And make it as big in the other direction as you want. So, as a quick corollary, we can make them arbitrarily large. But I won't write large because we haven't really defined what that word means. Now I'm going to talk about area or what, right? So, quick corollary. If one rectangle exists, then there exists two adjacent sides that are arbitrarily large. And I'll just state one more, I'll state one more theorem. I don't want to prove it. I'll leave the proof to the text if you want to look at it. I can sort of sketch out the very quick idea though, but if one rectangle exists, then not only can you construct arbitrarily large rectangles, but you can construct rectangles of any size that you want. So if someone gives you two sides and says, construct me a rectangle of this size, then you can do that. If one rectangle exists, then there exists a rectangle with two adjacent sides congruent to given line segments. Given line segments PQ and RS. All right, so you give me two line segments. So you just specify, here's a line segment, here's a line segment. Build me a rectangle with sides of this length so I can finish this construction and give you such a rectangle. So not just arbitrarily large, but any size that you want. The way you would do this, so I'll sort of lay out the method of proof. I won't go through it, but build as large a rectangle as you need. Right? Theorem above says we can do that. Take as large a rectangle as you need, and then draw in PQ along the sides. PQ and we'll also call it R and S. And then what you have to do, and this is a construction I actually want to go through next time to show you that you can always do this, but construct perpendiculars at those points. And then you just have to show, okay, well those three are right angles. Now you just have to show that this also is a right angle. And then you constructed such a rectangle.
Right.
So the details are given in the text if you want to take a look at it, but I won't go through that. What we're going to do next time is now a big deal. We're going to show that if one rectangle exists, then the angle sum of every triangle is 180 degrees. And that, of course, means that, well, have we proven that yet? No, we'll prove that too. We'll prove that if the angle sum of a triangle is 180 degrees, then then Playfair's postulate or the Euclidean parallel postulate must be true. So they're equivalent statements, which also means that the existence of rectangle is equivalent to the Euclidean parallel postulate. And I think it's a good place to stop. So we'll stop here a few minutes early, and I'll see you on Wednesday. There's 4 proofs for homework. If you have trouble with any of them, if you have questions, feel free to stop by my office or email me or whatever. I'd be happy to help.
I haven't looked. Did you post solutions for the exam?
Yeah, that's all I do.
Okay.